And we're live. Yes. Excellent. For 3 people. But that's okay. That's okay. I'm assuming in the next couple of minutes more people are going to show up, as they should. But welcome once again. I feel like this school year has been a little bit of a jip for some people, simply because they haven't been able to experience it the way that they, should have. I was just thinking about that because technically this is the last regular class period for Prob stat. And then the next time I see you on Monday, when we actually take our final exam for the period 1A midterm session, that will be the last time that we officially have class together. I don't know what's going on that Friday, the 29th. I have to look up that paperwork. Actually, no, I have it over here. Let me just take a look real quick. So according to this, Friday, January 29th, will be the first day of the new semester. So on Friday, the 29th, ProbStat will not be meeting, but you will be going to your third marking period classes starting on the 29th. That's cool. Yeah, the principal just sent out this letter to parents and guardians, so you guys probably should have this information as well, but we'll figure that junk out. We're going to get started in a few minutes. I just want to give people an opportunity to get in. Number one, to leave a comment in that chat for me. That'd be fantastic. Thank you. Wonderful. I'll remind you of that. Today is the last regular class period. Monday is your final exam. Now, the way that exam is going to work, just so we're all on the same page, the exam session on Monday, the 25th, is supposed to be from 7:10 to 9:24. It's supposed to be an hour and 2 hours and 14 minutes. That's weird. Yeah. Well, I guess they do allow a little bit of time for homeroom. Yeah, because 7:10, then we'll go to 7, whatever. We'll figure this junk out. But regardless of how you're taking it, whether you are going to be in class on Monday or you're going to be at home on the computer, the exam will be put into the Google Classroom stream, in which you will have a limited amount of time to get that thing done. I will have on Monday, I will have the Google Meet up and ready to go rather than the YouTube stream, because it is an exam period and I'm not actually instructing or anything like that. So I will do the Google Meet on Monday. Yeah. This has been the longest 2 weeks in the world. I am so not used to not seeing people. It's frustrating, to say the least. But I digress. Let's get started with what we're supposed to be doing. Now, for those of you who may not remember, in your Google Classroom stream 2 days ago, you should be able to see that there's the PDF file of the midterm, or actually technically now, the final exam review for ProbStat. We began working through that diligently on Tuesday, and we will hopefully wrap up everything that we need to wrap up today. So we'll figure that junk out. I don't know. It just feels like a very long race that has no end to it. That's what this whole thing feels like. One giant race that has no end to it. So if you would, have those PDFs open, have your notebooks out and open just in case you need to jot any of this stuff down. That would be fantastic, because obviously any information that I talk about and cover, I need to remember that for the final exam. Yes, absolutely. And then remember it or have it written down for the final exam. I'm going to bring the chat open on my phone here so that I can see what is going on in that chat right there. I did see a few people leave comments so far. Again, if you haven't left a comment, please make sure that you've left a comment. Come on, phone. Load it up. There it is. I see you all right there. Excellent. Let me flip my camera over and bring my calculator up. And this thing, chapow. Now you can see where we left off. This is what we were working on last time. And again, not being able to see it clearly, you need to use that PDF file that I put into the Google Classroom. We started looking through various things on the back pages. So I am going to jump around a little bit. We left off on number 9 last time. We left off on number 9 where I was talking about the different types of samples in the way that they could be taken. What constitutes a simple random sample? What is a systematic sample? Convenience, cluster, stratified, things of that nature. Just for the sake of argument, because I never actually marked it on the paper, but the answer to that particular question should have been systematic. A systematic sampling runs with the assumption that people would be entering or joining something randomly. For example, the order in which people enter a convenience store. Supposedly, if everyone leaves their house at a certain time and goes to this convenience store, I could sample every third person coming in the door, and that would technically be random. More specifically, a systematic random, because it would be like, okay, 1, 2, that person, sample that person, 1, 2, sample that person, if I decided to do every third person. So a tax auditor selects every 1,000th income tax return that is received. Don't forget to fill out your taxes this year, by the way. I've already started mine. You really should start yours as soon as humanly possible. The sooner you start it, the sooner you can get a refund, unless you guys don't get refunds, in which case I'm sorry. Anyway, back to this. Number 10, because I wanted to hit up all of the early stuff first and then go back to the probability. A market researcher obtains a sample of 50 people by standing outside a store and asking every 20th person, we just talked about this, every 20th person who enters the store to fill out a survey until she has 50 people. What sampling method's being used here? Will the resulting sample be a random sample? Will it be a, quote, simple random sample? I want to distinguish those. And then it says to explain your thinking. Well, everything that we just talked about, this number 10 is a systematic sampling. There's a bit of issue with that. I mean, if you want to sample 50 people and you're doing every 20th person, I mean, it doesn't take that much to figure out that like have to go through like 1,000 people before you got your sample. So I don't know how long you're going to be standing there for. But it is definitely systematic. Is it random? Yes, technically it is random because of the order in which people show up to the store. They technically show up randomly. There are some people who may not ever get sampled. People who are like always there when the store opens or something like that. They'll never be the 20th person. They'll always be like the first or second person. But will it be simple random? Hold on, there's an announcement. Cool announcements interrupting my class. Great. Anyway, will it be simple random? No. This thing will be random, but it will not be simple random, because simple random sample has a very distinctive definition. In a simple random sample, every person or groups of people have an equal chance of being selected. And if you are selecting every 20th person, as I mentioned, what about those people that always show up early? If you're always showing up early or always being the first one when the store opens, then technically, according to this, you'll never be sampled. You'll never be sampled. I don't know. There's a similar idea that you could do with like a phone book. I don't know if you guys know, phone books used to be these giant books that people had where you probably already know this, but I'm going to say it anyway. But phone books used to be this thing where you get like an alphabetical listing of everybody in your region or area or county, and you can get all their phone numbers because they're all in the phone book. Nowadays, like the phone book is nowhere near what it used to be. It used to be the giant thick thing. But I digress. If you were to go into the phone book and you were to select every like 100th name to sample that person, okay, yeah, that technically could be a random sample, but it's definitely not simple random, because if your name is Aaron A. Aronson, then you're never going to be selected because you're always going to be first in the phone book because the person's only selecting every 100th person. I don't know. A gold star to the person who can tell me what I'm referencing when I say Aaron A. Aronson, just because that's a pretty deep cut reference. Anyway, number 11. Oh, excuse me. I'm not sick. I'm not. Leave me alone. Number 11. At a school, there are two different math classes of the same age. The two classes have different teachers. The school principal is interested in gauging the effectiveness of two different teaching methods and asks each teacher to try one of the methods. At the end of the semester, both classes are given the same test, and the results are compared. In this experiment, what is the factor imposed on the participants, and how many levels in those factors? Now, in terms of experimental design, this is definitely an experimental problem. They are imposing a treatment on the participants, I guess you could say, if you're using proper terminology. But what is the factor being imposed, and how many levels are in those factors? Well, the factor being imposed is the teaching method. Now, we don't know what these teaching methods are. The only thing that we know is that there are two different ones. So what is the factor being imposed? It's the teaching methods. How many levels? Well, there are two levels. There are two levels. Teaching method 1, teaching method 2. I don't know. But there is a major flaw. And the question even asked that. Explain what the major design flaw could be in this experiment. When you have an experiment, one of the most important things that you must do is keep everything as similar as possible between two different groups. For example, two different math classes. You have math class 1, math class 2. And you're imposing these teaching methods on these kids. Cool. Everything needs to be kept the same. The time of year, the type of tests that they receive, how much homework they receive, perhaps even the time of day they take the class. I don't know. The number of kids in each class. I don't know. You have to try and keep everything as identical as possible, with the exception of the treatment being imposed. And in this case, the teaching methods. Now, that should be the only difference. But the major flaw is you have two different teachers. You have two different teachers here. I mean, you guys know when you have one teacher over another, they teach slightly differently. And some people mesh with one teacher and don't mesh with another teacher. Now think of that in terms of a boss, It's like, oh, I really got along with this boss. I did not get along with this boss. That's life. That happens. But because of that, that is the major design flaw. Because maybe the teaching method kind of leans into one of the teacher's abilities and the other one doesn't. So one might be more effective simply because, oh, this is right up my wheelhouse. And then they do really well with the teaching method. But then the other one's like, yeah, I'm not really comfortable with this teaching method. And then they suck at it. And then the kids suffer as a result. In an experiment, everything must be kept as identical as possible with the exception of the treatment. Okay. I'm on the back, or technically the back. It's the 4th page. I want to do these problems, and then I want to backtrack to the probability problems. I wanted to do the probability problems last. But I got to remind you of something here. So let me get a blank piece of paper. I got to draw something out for you. At one point during the school year, we dealt with the normal curve. The normal curve, that's okay, I guess. Yeah, I'm trying to draw it as best I can there. The normal curve is a bell curve. Unimodal, symmetric, that kind of thing. And when you have a normal curve, you could potentially be dealing with z-scores, as we just saw in number 12. And I'm actually going to draw out something here for number 12. Typically, if you are just dealing with a basic standard normal curve, then right in the middle you have 0 for a z-score. I'm going to remind you of what z-scores are. And then at equal intervals, moving up here, you got z-scores, 1, 2, and 3. And to the left, you got z-scores -1, -2, and -3. These z-scores represent the number of standard deviations you are away from the mean, which is right in the middle. This is a reminder of what we did in the past. In fact, a z-score is calculated typically in the following way. The data point minus the mean divided by the standard deviation. Now, this kind of goes into the nuts and bolts as to what the z-score is truly all about. There is a very easy way to do it on the calculator, which I'm going to walk you through in a few moments. I just want to try to remind you as to what we did back in the day, because hopefully some of this is coming back to you in a big way. There was something called the empirical rule as well, in which between certain z-scores lay a certain percentage of the data points. So, for example, if the population of Americans, I don't know, IQ scores or some junk like that, I don't know, we're on this particular chart, and we were able to calculate z-scores for people's IQ. If you were between -2 and +2 standard deviations away from the mean, and you figured out what those IQs should have been, then you would actually be capturing 95% of the population, a giant slice of that population. It's a weird kind of thing. We had a function in the calculator that did this for us, and I want to bring your attention to the calculator at this point. Obviously, you have the calculators on your Chromebooks. I'm going to bring my calculator up on my screen. Let's see here. Click. Let me just clear this out. There we go. Make it a lot easier. To remind you as to where things are, again, second vars will take you to where that normal CDF is. That normal CDF is what we are interested in, not the PDF. And just for the sake of argument, I'm going to change this lower and upper. I'm just going to show you what this would calculate to be. If I went -1 to +1 and didn't change anything else, the calculator would automatically assume that I'm dealing with z-scores. And since I'm dealing with z-scores, again, according to the empirical rule, approximately 68% of the data. I'll do the same thing with a 3 or a -3 to +3, (99.7% of the data. So that's exactly what it's calculating. It's calculating the proportion of the population that you're trying to capture. It's also technically calculating the area that you could shade in under this curve. It's very strange. But now I bring your attention to number 12. Number 12. If z is a standard normal variable, find the probability that z lies between those two data points. I'm going to go to my calculator with this one. Go to my calculator. I'm going to do a normal CDF. I'm not going to change the mean or standard deviation. I'm going to go from negative 1.10 to negative 0.36. Not going to change anything else. There we go. 0.223. Technically that rounds up to 3.8, but if you ignore rounding, then it's 0.2237. Make sure you understand what is going on with this normal CDF. Whenever you input stuff, typically you got to do a lower limit and an upper limit, and then a mean and a standard deviation. If you leave the mean as 0 and you leave the standard deviation as 1, then it automatically assumes you're calculating z-scores. Let's compare that to number 13, because number 13 is going to take it in a slightly different direction. Move that up to the top. Yeah, come on, zoom out. There's more words. There we go. A bank loan officer rates applicants for credit. The ratings are normally distributed with a mean of 200 and a standard deviation of 50. Just write that down for the sake of argument. A mean of 200 and a standard deviation of 50. There we go. That's going to be helpful. Now it says to find the score which separates the lower 60% from the top 40%. Let me show you what that means, actually. Let me show you what that means. I'm going to draw the normal curve one more time. That's okay. Normal curve. Now, the thing you got to know right here, this point right here, yes, that's the mean. But that is also the 50th percentile. Right in the middle is the 50th percentile. Now, I don't know exactly where all the percentiles are. I can only estimate. But this particular problem wants you to find the score which separates the lower 60% from the upper 40%. And the idea being is that, well, again, I'm just going to shade this in for the sake of argument. By the way, the shaded in region, if I stopped right here, I would have shaded in 50%. And let's just assume right there, that is 60%. And this blank spot right here is 40%. I'm going to reread the question. The ratings are normally distributed, blah, blah, blah. Find the score which separates the lower 60% from the top 40%. That's what this question is really going for. They want to know, what is the data point that separates these two percentages, 60 and 40? Now, something I wrote down quite a while ago. With normal CDF, you input data to get percent. You can't see what I wrote. There you go. With normal CDF, you input the data to get the percentage or the percent. But With inverse norm, you input the percentage to get the data. It's an inverse function. Zoom out a little. There we go. Normal CDF, you input the data, you input the lower and upper limits in order to get the percentage between those points. However, now with inverse norm, you are going to input the percentage in order to get back the data. It is the reverse function. If you go to your calculator and go back to second vars, you should have this option called inverse norm. I'm in the wrong function here. Get out of there, function. Quit. There we go. Second vars, inverse norm. There we go. Much better. The area that I shaded in on my curve was 60%. So I'm going to put in 0.60. Meaning, well, I want to know, okay, where the lower 60% is cut off where? At what data point? With an average of 200, which I wrote down before, and a sigma of 50, which I wrote down before. Now, typically, I keep my tail on the left. On the TI-83 calculator, it's automatically set and you can't change it. I just keep it to the left, especially considering the fact that with my picture here, you can see that I shaded in everything to the left. And when I did that, that left side equaled 60%. That's the data point. Now, I remember there being a little bit of a typo in the answers, but the answer that you see on my calculator right now is indeed the exact answer. It is the exact answer, 212.67. If I go back here, yes, technically this is the closest one, but it was 212.67. So find the score, 212.67, that separates the lower 60% from the top 40%. And that does make sense because if I go back to my picture here, the 50th percentile would be right at the average of 200, and the 60th percentile would be 212.67, which obviously is higher than the mean. Oh, these data points. Let's take a look at number 13. Or I'm sorry, 14. The weekly salaries of teachers in one state are normally distributed with a mean of 490, a standard deviation of 45. What is the probability that a randomly selected teacher earns more than 525 a week? This is a normal CDF problem because they give you the data and they want the percentage, or in this case, the probability. This is a normal CDF problem. Now, the way that it's going to be written out, you'll see it's slightly different in the calculator. But the way that this is normally written out, lower limit, upper limit, 525, comma, some big number. I don't know what that big number is. Move that out of the glare. There we go. I don't know what that big number is. I might just put like 10,000. No, like 100,000 or something like that. I don't know. But then with a mean of 490 and a standard deviation of 45. That's the order in which that stuff is typically typed in. But again, with your calculators, they do offer that interface where you put those numbers directly in the locations where they belong. So if I went second vars, normal CDF, lower limit, upper limit, I don't know, just put some giant number. Doesn't matter what it is. 490, 45. All right. There it is. 0.218, which technically, again, a little bit of a typo in the choices, but that D should have been the selection there, which I did circle. Now, the biggest question for this type of problem people usually ask me is like, well, how do you know it's 525 big number? How do you know that it's going like that? Well, it's based on the question. What is the probability that a randomly selected teacher earns more than 525, meaning 525 or more, 525 or greater? That higher number, that upper limit, you don't really know what to put it at, so you just put like some big number just to kind of encompass everything. You don't want to put something that's close to 525 in fear that it would, well, calculate the wrong percentage. This guy asked the question, why? Oh, did I make sense? I think I answered it without even looking at her question. I hope that's the case. Give me a thumbs up if that's the case. If I answered it without actually reading your question first. There we go. Good. What's interesting, it's like, check this out. I'm going to do it again. But I'm going to put like, I'll decrease the number of zeros. I'll put like 100,000. And if I paste that, you can see the number doesn't really change. But then the closer that 100,000 number gets to 525, let me make it like 1,000. There we go. The closer it gets, it didn't change all too much. No, it didn't really change. I guess it's just based on the average and the standard deviation, really, because basically on a normal curve, the farther you go out to the right or to the left, in this case, the right, the farther you go out, the smaller the number of data points actually exist that far out. So as long as you just hit some big number, it just kind of encompasses all of that curve. It's kind of weird, I know. But that's why I just write big number instead of actually putting it like, 100,000. Like, no, I just write big number because then I just assume, it's a big number. In this case, if you wanted to do 525 or less, this is actually a good example. If I wanted to do 525 or less, I would have to put 525 in the upper category. And then for the lower category, I just got to put some giant negative number. Again, not really caring what it is, but it's just got to be some kind of like, I usually write small number, comma 525. Boom, which gets you that answer. Which coincidentally, that number is the complement to the answer that we just got. It is the complement to the answer that we just got, which kind of parlays very nicely into probability. So I'm going to back up a little bit in this review, and I am going to jump to number 2. And in order to do number 2, I am going to draw something on paper. So I'm going to read number 2, but I am also going to draw out what I'm reading. So again, you can read this in the PDF that I posted to the Google Classroom stream. But I'm going to read it and draw it out. According to a recent census, about 13% of the general population are seniors 65 years of age or older. Okay? Medical reports saw that 14% of the seniors get the flu each year. On the other hand, about 25% of people under the age of 65 get the flu each year. Okay, watch what I'm about to do here. Let's see here. 0.7, cool. I'll explain what I did after I finished drawing it in a moment. There we go. That should do it. So let me reread the question and kind of point out what the heck I just did. According to a recent census, and I'm going to point at the same time, by the way, about 13%, I'll point with my pen, here we go, 13% of the population are considered to be seniors. Now, what that implies to me is that 87% are considered not to be seniors. Then it says, it shows that 14% of the seniors, meaning, oh, now that I've already randomly selected a senior, there is a 14% chance that they get the flu each year, and an 86% chance that they don't. On the other hand, of the people who are not seniors, 25% of them get the flu each year, and 75% logically should not. That actually answers part A. Draw a tree diagram. Then they ask a bunch of questions, which we'll get to in a moment. But this is the proper organization, I should say, of these probabilities. I can go down each branch of this tree and answer a slightly different question depending on how they word it. So number 2, part B. What is the probability that a person selected at random from the general population is a senior who will get the flu this year? What is the probability that a person selected at random from the general population is a senior citizen who will get the flu this year? Now, the wording of this is very precise. There are 2 specific ways that you could interpret number 2, part B. There's 2 ways you could technically interpret it, and I want to be very clear about which one it actually is. So I'm going to zoom in right here real quick and show you how the tree diagram can help you answer that question. One way to interpret this question, what is the probability that a person selected at random is a senior citizen who gets the flu? One way of doing this is, okay, it's the probability of being a senior given they got the flu, or it's the probability that they're a senior and they got the flu. Let me write something on the board here, because depending on how we interpret this question will change the way that we calculate it. If we say it's the probability of being a senior given they have the flu, we would then have to use a certain formula that would be provided for you, of course, where we would have to calculate senior and flu divided by the probability of flu. Ugh, that's kind of painful. Or the way that this could be interpreted is the probability of senior and flu, which would just be the probability of being a senior times the probability of getting the flu given that you are a senior. It's a weird type of distinction. Which one is easier is usually the question I get. What would be easier is if we got that word and. If we interpreted it as and, which part B actually is that one. The way that I've taught you how to do probability with the words and versus or is understanding the distinction between multiplication and addition. When it comes to the word and, I want you to immediately think about multiplication. Oh, the probability of A and B? Oh, I just got to take the probability of A and multiply by the probability of B. Yes. Yes. If it's or, there's a slightly different connotation to it. If it's or, you would have to do the probability of A plus the probability of B plus, I said, minus the probability of both. And again, that formula would be provided for you. But in this case, part B, I would interpret that thing as a senior and getting the flu, which means that if I go back to my probability tree where I organized all of this information, the only thing I would have to worry about is walking along these branches, point 13, point 14, and multiplying them together. Multiplying those together, I get 0.0182. 0.0182. So let me go back to my little paper here. Zooming in. The probability of a senior and flu, where I would multiply 0.13 times 0.14, gets me 0.0182. A senior who gets the flu would be a senior and sick with the flu. Then we read part C. What is the probability that a person selected at random from the general population under the age of 65, meaning not a senior, will get the flu this year? Well, this is, okay, probability of not a senior and getting the flu. Well, thankfully, we organized our information into this tree, because not being a senior and getting the flu, I would multiply those two numbers together. Oh, you can't see it. There's giant glare in the way. There we go. Moved it a little. But not being a senior, we figured out by the tree, we organized it, and getting the flu, we would multiply those two numbers together, 0.87 times 0.25 to get you 0.2175. It's not entirely obvious that you'd get those numbers just by reading the problem first, which is why they suggested that you do a probability tree in order to organize that information. And then once you did, then it's a bit more obvious, like, oh, okay, I multiply those two numbers together. So let me actually do that here. Zooming in, there we go. The probability of not senior and flu would be 0.87 times 0.25, which would be 0.2175. There is a formula that you need. Actually, let me write down all the formulas that you technically would need for the probability section. Let me just write these down for the sake of argument, just so we have them written down. First, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Zoom out a little. There we go. There actually was a definition that went along with this. It used the words mutually exclusive, or it used the word disjoint, which those two phrases mean the exact same thing. Mutually exclusive and disjoint mean exactly the same thing. What it means is if the probability of A and B is equal to 0, meaning there's nothing that they have in common, there's no way that both events can happen at the same time, then A and B are mutually exclusive. Another way of saying that is disjoint. They are mutually exclusive. It's like a Venn diagram that has no overlap in the middle. There's nothing in the middle. There's no way that both events can happen at the same time. You draw one card from a deck of cards. What's the probability that you get a heart and a diamond? Well, you can't do that with one card. Okay, then those two events are mutually exclusive. But then there was the probability of A and B. A and B, there was actually two ways of calculating it, depending on if the events were independent or not. If independent, then it would just be the probability of A times the probability of B, if they were independent of each other. If not independent, then it would be the probability of A times the probability of B given A. Now, that given statement is interesting. It's like when you did probability problems back in the day and you were picking marbles from a bag, and the teacher decided to use the phrase with replacement or without replacement. With replacement, meaning you put the marble back, means that the events of picking marbles are independent from each other, meaning the previous pick does not affect later picks. But if you don't put that marble back, then, well, later picks are affected by previous picks, and they're not independent. And that probability of B depends on what happened with the previous event of picking with A. Furthermore, there's usually one more big formula that they give you before I finish up these these probability questions. I wrote this kind of on the board earlier, but I wanted to write it down again. It's the probability of B given A. If you ever have to do something like that and you don't have enough information to get it done, typically this is the calculation that would have to take place. You take the probability of A and B and you divide it by the probability of A. Now that goes hand in hand with the next question. Number 3. Zooming in, zooming in, zooming in. 50% of seniors take a math class and make the honor roll. 75% of seniors take a math class. If a senior is selected at random, what is the probability that the senior makes the honor roll given that they're in a math class? Okay, hold on. Zoom out, zoom out, zoom out. What this question is really asking is this. What is the probability that they make the honor roll given they are in a math class? This is what the question is asking. And in order to do that, I'm going to follow the formula that I have written at the top, where the probability of honor roll and math divided by the probability of math. Well, honor roll and math, they told me, was 50%. And taking a math class was 75%. That is what I would have to calculate. The answer is approximately 0.67. It rounds. But that's how that problem would be done. You would need to know that formula at the top and recognize that it is a given problem. A conditional probability is what they call it. Let's talk about number 4. Number 4 is talking about Venn diagrams. I love me some Venn diagrams. Number 4, Mrs. Face. That's funny. Has a class of 25 students. Sorry, it's just Mrs. Face. I just go in every day, be like, your face. Anyway, 11 of our students play Brood War only, while 3 play Brood War and Diablo. 5 of our students play no games at all. How many students play Diablo only? Make a Venn diagram. Okay, hold on. This would be Brood, and this would be Diablo. There we go. Let's zoom in on that sucker. Okay. 11 of our students play Brood War only. Okay, so 11. 3 play both. 5 play no games at all. How many of our students play Diablo only? Oh, well, there's 25 kids. 11 plus 3 plus 5 is 19. Should be 6. Yeah, there's the Venn diagram. Sometimes it's just a matter of labeling things out. A lot of the time they do give you like the probability of such a thing, you know. In fact, check this out. How many kids play Brood War? 14. 14 play Brood War. How many play Diablo? 9. 9 play Diablo. How many play Brood War or Diablo? That would be, well, technically 14 plus 9 minus 3 if you're sticking with that formula. Or if you have the Venn diagram, it's just these 3 numbers added up together, which is kind of nice. I like it. I like it a lot. All right, but let's actually read the question. What is the probability that a student chosen at random plays no games at all? Now they want a probability. No games at all, that would be 5 divided by 25. The probability of none, 5 over 25. What is that? 1/5. So it's like 0.2. Yeah. And then what is the probability that they play one game only? Well, one game only. Remember, the 3 in the middle play both games. These 6 only play Diablo. These 11 only play Brood. 11 plus 6, 17. 1 only would be 17 out of 25, which would be 0.68. Love it. I can't see it. Zoom out. There we go. Oh, look. A bag containing beads. Nice. Well, I'll just say very briefly, because I know I'm running a little short of time. I'll just say briefly in regards to number 5. There's experimental probability and there's theoretical probability. Experimental probability, no. Theoretical probability is what could happen. Theoretical probability is what could happen or should. I don't know. Experimental probability is what did happen. Now, theoretical and experimental don't necessarily always line up with each other. In the long run, they're supposed to. As the number of trials increases, then yes, the experimental probability should be approaching theoretical. But until then, it could vary by any which number of ways. They're saying a bag containing green and yellow beads. You pull a green one from the bag, note its color, and replace it, meaning you put it right back. After 200 trials, you have 1,270 green and 730 yellow. That should have been after 2,000 trials. I think that's another typo there. And then what is the experimental probability of pulling a yellow bead? Well, 730 out of 2,000. And then you give me the decimal. And then finally, let's talk about this. If the probability of drawing a jack from a standard deck of cards is 4 out of 13, is that real? That can't be real. Oh, it says if. Okay, it says if. I don't trust this problem. And the probability of drawing a spade is 13 out of 52. Okay. What is the probability of drawing a jack and a spade? Yeah, I'm going to have to change that number. I don't like that number. Hold on. Zooming in, zooming in, zooming in. Where is it? Where is it? It'll focus in a moment. The probability of drawing a jack from a standard deck of cards, I think that's a big old typo there. I'm going to have to fix that. It's 4 out of 52. But this number really should be. I'm going to change this. I'm going to have you change this as well. That should be 1 out of 13. That should be 1 out of 13. What are they even thinking? Now, picking a spade, yes, is 13 out of 52. Good for it. But they want to know what is the probability of drawing a jack and a spade. Now, it says, are these events independent of each other? Well, how many jack of spades are there? There's only 1 jack of spades. That's interesting. Hold on. Let me write something down here. Probability of jack and spade equals, well, a jack is 1 out of 13 times a spade is 13 out of 52. And if you multiply those two fractions together, that's 1 out of 52. Are these events independent? I'm not going to worry about that question. I'm going to say cross that question out. That's not very much important at the moment. Not to mention, if I were to get into those details, that would take me a bit longer than the amount of time that I have right now. I don't like that question. Anyway, we're out of time. If you have any remaining questions for me, please make sure that you are emailing me. If you did not leave a comment in the chat, please make sure that you do so. I've seen the ones of the people that have left them so far. Please make sure that you have left that. On Monday, the exam period is at 7:10, but I don't plan on starting till about 7:20-ish, 7:25-ish. So for those of you who are online, I will be doing the Google Meet on Monday. But all of that information will be in Google Classroom as a reminder to you once we get closer. Yay. Anyway, bell's going to be ringing. So I'm going to sign off. Bye-bye. 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 Bye-bye, everyone. Bye-bye. I'll see you all on Monday. Bye-bye. 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 Goodbye, everyone. Bye-bye. Bye-bye. I'm just pointing. Bye. Okay, whatever. Go to your next class.